So we went over KCL, or Kirchhoff's current law, or Kirchhoff's first law, and now we are going to go over Kirchhoff's voltage law, or Kirchhoff's second law, or the mesh analysis basis. Basically what mesh analysis is based on. That's maybe the better way to say it. Okay, so much as with Kirchhoff's current law said that all of the current in and out of a single node had to equal to zero, Kirchhoff's second law, KVL, Kirchhoff's voltage law, says that all of the voltages in a loop need to go up or down in such a way that the sum of all of them equal zero. Now this is pretty interesting because for me, Kirchhoff's current law has always been much more intuitive, but I've talked to a lot of other electrical engineers who think that Kirchhoff's voltage law is a lot more intuitive, so it's up to you. We'll see exactly what happens and what you think. So let's just give a quick example of what I'm talking about here. So draw some ugly circuit here. We can even do another, wow, just ignore that one in the corner there. So basically what we are saying here is that if I need to put a voltage source in here. This isn't going to make any sense. What I'm saying here is that if there is a voltage going up in each one of these loops and voltages going down, then they all have to equal zero in the end. So, wow, this might have been a terrible mistake. Moving forward. So as we go up in voltage across here, we can assume that we're going down in voltage right there. So the summation of the voltages up and down here are zero. And then since we're expecting a voltage drop here, we should be able to see that we are going to be increasing or dropping the voltage in such a way that all of the voltages across these three resistors are also equal to zero, and same with this one. And that is the basic premise, is that basically whatever mesh you have, the sum of all of the voltages up or down across the different elements should equal zero. Now this is something that we touched on very briefly when talking about branches, nodes, and loops, is that when we are doing this, it has to be a loop that doesn't include any other loop. So you can't go like this and have it make sense, because then what are you doing with that resistor? So even though a loop technically is with everything, in a mesh analysis, you have to be certain that none of your loops actually include any other loops. So this is, again, the basic idea that as for mesh analysis, as you're going through it, you will say, okay, I know voltage across that's going up, voltage across that's going down, and then that's going to equal to zero, and then you just set that up mathematically, and you come up with a solution. And that's really it. So I created another couple of steps. I made one modification from the KCL steps that I had, and I included one final step explicitly in there. But in general, it's fairly similar to what we did with KCL. But let's now do it with KVL. I'm going to set up a sample here. We'll go over those steps, and then we'll apply them, and then we'll do another sample, and then we'll be ready to go. Again, if you have any questions after doing this, after the video is done, this is also available as a written tutorial with even more samples on circuitbread.com, so go check it out there. If you have any questions or comments, put it there, and that will help you even better understand what's going on here. Okay, so now we have this set up, and again, this is another one of those very simple things that depending on what we needed, we don't necessarily need this advanced analysis to figure out what we want, but this is just a good way to step through it. So our very first step is going to be, just like with KCL, take our time, look at what we have, look at what we need to find out. If we have a specific problem given to us by a professor or by our bosses, figure out, okay, I need to find out that current or that voltage or that power, and then start figuring out, this is what I have, this is what I need, this is some of the assumptions we have, and this is some of the intuitive understandings that I have of this problem. Then the second thing that we do is we assign the direction of the mesh current. So I can say that I think the current is flowing this way, so I'll do it that way. But honestly, it would work just as well if you went this way. Just everything would be backwards. And then you'd just be defining it backwards, but everything works out in the same. But the thing is it has to be consistent. So if you have a much more complicated circuit, you need to make sure you identify the direction that the current is flowing, and then make sure that your equations match that assumption, or else you're going to have some serious issues. Then the next step is basically to come up with an equation that represents your current there. So you're going to see how your voltage drops or increases over each thing, and then make that equal to zero. Yep. In this case, we would look at this and see the voltage is increasing over there, dropping over here, dropping over there. And we will get into that when we're doing the actual sample, that there is 2 different ways of looking at that, and they're fine however you do it as long as you're consistent. But for right now, we'll just say that step 3 is, again, figuring out that equation and figuring out how they're all equal to 0. Is that step 3? No, yes, it is step 3. Sweet. Okay, I got that right. Then once you have all of your equations for step 4, you set them all up and you solve for them. Your simultaneous equations, if you have multiple loops and multiple unknowns that you're going to have to work through them. Again, you can either do that algebraically, or you can set them up in a nice, beautiful matrix setup and then put it into some sort of matrix calculator or into your calculator to basically solve that all, which is something I highly recommend if you're capable, because if you're like me, you're going to mess up in the math, and it's just easier to eliminate or decrease the amount of math as much as possible, or you could practice and become a better person. That's not a bad idea either. But that is what that step is, to solve those simultaneous equations and get actual values for either the voltages across these or the currents through them, depending on exactly what you are looking for. And then finally, the 5th step, step 5, is the sanity check. And this is the one that from KCL I decided, let's just make that explicit. Take a moment after you're done to look at it and say, does this make sense? Do these numbers make sense? If I have a 10-volt power supply and I see 100 volts over R2, where would that voltage come from? That doesn't make any sense. Obviously, I made some sort of mistake with my math. If I have a 10-volt power supply and I see 10,000 amps across it, like, okay, 10 volts using Ohm's law, that just doesn't make any sense. So that final step should be, if you aren't, and even if you are, using your matrix calculator and LT Spice to double check your work, take a moment to say, does this make sense? Do these numbers work? If I have a bigger resistance, should I have a bigger voltage across it if it's sharing current? If I have a smaller resistance and it's in parallel with something, does it have a larger amount of current going through it? Those sorts of questions that, 1, will make it so you're more likely to find out if you screwed up your math, and 2, helps give you a better intuitive understanding of what you're doing. And that is the 5th step. Okay, so with that, let's actually go through those steps. And our first step is to look at this and say intuitively what's going on. So we have a voltage source, we have 2 resistors, and we know that since these resistors are in series, that the current through them is going to be the same. And since the current through them is going to be the same, and this is a larger resistance here, and that's a smaller resistance there, we can anticipate that our voltage drop is going to be larger over R2 over R1. So now that we have an idea intuitively of what's going on, and again, looking at these, we should know that our current is probably going to be in the couple of milliamps, nothing that great, because we have about 1200 ohms in series here. So we're expecting a fairly low thing. So now we can go on to the next step, which is basically just assigning the mesh currents. So with this one, since we only have this single mesh, I'm going to say that the mesh current is going this way, and I'm just going to call it I1. So we've now looked at it and we said, all right, I expect that to go that way. Now on the next sample that we're going to do, I'm going to show how with multiple meshes it gets a little bit more complicated. But for right now, that's really all we need to do for step 2, is just say I1, we're assuming it's going in this direction. Now the third step is creating the equation that explains all of this. And this is kind of where it gets to be a little bit more challenging, because I will show it to you in 2 ways. And one way is more intuitive for me, and one way has been more intuitive for the other engineers that I've worked with. So let me go with the way that is more intuitive for other engineers. So looking at this, you're assuming that current is flowing this way, so you're assuming that your voltage is dropping like this. So now as you are getting that current flow and you're creating your voltages, you will have that flow and you'll come up to this element and you'll say, I see a negative number there first. So my first thing will be negative 10 volts. And then as I keep on coming up here, I see that I have a positive there. So I'm going to be adding this voltage, which we know that the voltage is equal to the current times the resistance. So this is just going to be I1 times R1. And then since we're continuing in our loop, we see that plus sign again. And so we know that's going to be a plus. And we know that I1 times R2 is also going to give us our voltage there. So that gives us 0. And I forgot to put Ohm's law up there in the corner, which again is something I always use. That I don't know why, it just helps me. It helps keep me straight when I do things. So that is the first way to set that up. And for some people, it's very, very intuitive because they come and they see the negative sign, so they know -10. Then they see the positive sign, so plus that voltage. And then that is plus that voltage. And again, when I say voltage, even though it's current times resistance, so you think, wait, where's the voltage? Again, because of Ohm's law, that is the voltage. So that is why it's Kirchhoff's voltage law. Now the way for me, it's more intuitive, and I don't know if it's right or wrong, whatever. For me, I see the current going up in voltage. So for me, I would say, okay, that's 10 volts. And then, hey, it's dropping across this resistor. So I would subtract I1 times R1, and then it's dropping across that resistor, which is I1 minus R2. And then that equals 0, which if you look at those are mathematically the exact same because you can just multiply 1 by -1 and it gets you the same thing. So as long as you are consistent in the way you do it, it's totally fine. And whichever one makes the most sense for you, that's fine. I think with this one, with the first method, you just need to make sure that you are assigning those voltages properly and having them match the current, or else you're going to really mess things up. So with that, we have the circuit, everything is set up, and now we can move to the next step. Step 4 is basically just solving for all this. Now we only have one equation, so you can't do all the simultaneous equations, but it's basically what we need to do. So R1, we have that. We know that R1 is 500 ohms. We know that R2 is R2 is 700 ohms. So now we know 10, oh wow, why is that a V? Let's just try that again. So now we know 10 minus 500 I1 minus 700 I1 equals 0. So then we can basically just move those over to the other side and say 10 volts equals 1200 I1. And so we have 10 over 1200 volts over resistance equals I1. There we go. So 1/120th, which what does that come out to in decimal? 0.0083. So 0.0083 amps equals I1, or 8.3 milliamps equals I1. And now you can solve for V1 by sticking it in there, or V2 by sticking that current in there, and that's all you had to do. So again, this is a really simple setup, just something we did so we get used to the flow. We need to do that final sanity check. So as I mentioned earlier, we're expecting 10 volts. We're expecting 10 volts over approximately a little bit over 1,000 ohms. We're going to be a little bit less than 10 milliamps just because we have 10 over 1,000. So this number is in the right area, order of magnitude, so that at least makes sense. It's a positive number, which makes sense because we're expecting current to be positive flowing in that direction. So overall, this seems pretty good. And so with that, let's go to the next sample, which is going to be just a little bit more complicated. Okay, so this is the second sample, and as you can see, it's a little bit more complicated. We have 2 voltage sources, and we have an additional resistor here. And as looking at it, we can tell that we are going to have 2 loops here, because if we did one full loop, we'd be missing that R3. We have the same voltage sources here, 10 volts over there, so they're not the same, but the same voltage amount on these 2 sources here. And then we have a lower resistance here and a higher resistance here, so we should expect the current to be a little bit higher through R1 and through R2. And then whatever our current through R1 and R2 is, we should expect to see that current through R3. So R3 should be the sum of R1 and R2 at the end. So if we do everything right and our math comes out, that's about what we're expecting. And again, since these are in the hundreds of ohms, we should expect something in the low 10s to 20s to 30s of milliamps. And so if we get anything that's absolutely huge or absolutely tiny compared to that, then we know that we messed up our math somewhere. So that's what we're going to get from our first overlook, our first step. So our next step is basically just assigning that mesh current. So just like last time, I'm going to go in a clockwise direction and call that I1. And then for this one, I'm actually going to keep the same direction just because I like to go clockwise, even though I think that the current will be flowing there. And again, since as long as we're consistent, it should be fine. I just know that I2, the way I'm assigning it, is almost certainly going to be negative, so I2. And just in case you can't read my terrible handwriting, R1 is 300 ohms, R2 is 700 ohms, and R3 is 100 ohms. Okay, so now on step 3, we are going to solve this doing the exactly what I talked about before. I'm going to use the first method discussed, so I'm going to assume current is flowing this way for I1 and this way for R3, and I'm going to say that should be negative 10 volts plus, let me get my V equals IR there, plus I1 R1, so let's just do 300 I1, skip a step there. And now this is where it's kind of interesting because now I'm expecting current to go through here, but that's being shared with this side over here. You have to take into account the fact that you have current flowing this way with I1 and current flowing that way with I2. And so you can do that mathematically by saying, okay, I know what R3 is, that's 100, so I'm still assuming on this side that it's plus minus, so that's plus 100, and then it's going to be I1 minus I2 equals to 0. So that is our first equation, is we have 10 volts right there, then our voltage drop there, and our voltage drop there, assuming that I2 is going in the opposite direction through that resistor. So that's the key thing that I wanted to mention with this, is when you have a shared element there, that you have to take that into account with your math with I1 minus I2 in this case. So now on the other side, we have the exact same thing. Let's just assume that we start at our 10 volts again. So we have 10 volts because we are seeing that plus there. But since our current is flowing this way, now from this perspective, we have plus minus. So that's going to be nice and fun. So we have plus I2, or excuse me, plus 100, and then it's I2 minus I1. And then here, since we're assuming that's plus and that's minus, because we're assuming current is flowing that way, then we're going to have a plus I2, 700 I2 equals 0. So a couple of the key things to notice here is that even though on the outside these are both plus 100, since the current was defined as going a different way, you have the differences in the back, in the middle. So on this one is I1 minus I2. On this one, it's I2 minus I1. Now, if we defined going the other direction, that would have been flipped, but we didn't. So don't change your math. Figure out which direction you're going, stick with it. Don't mess with it. Okay, and with that, now we want to actually, for our fourth step, to solve these simultaneous equations and to simplify things. We'll take that first one and we'll just say negative 10 volts plus 400 I1 minus 100 I2 equals 0. And then that second one, we will say that is 10 volts plus 800 I2 minus 100 I1 equals 0. Now, instead of going through all of the algebra, how about we just set this up in a way that we can plug this into a matrix calculator? So I'm going to take that and I'm going to say 400 I1 minus, that's also where I make a ton of my mistakes. Is I literally said out loud I1 and wrote I2. Then 100 I2 equals 10 volts. And then on this side, I'm going to say negative 100 I1 plus 800 I2 equals negative 10 volts. And so now you see I have I1, I1, I2, I2, and then my in voltages there. So I can use these to just say I can put 400, negative 100, and 10 into my matrix calculator, and then negative 100, positive 800, and then negative 10 in my matrix calculator, and let's see what comes up. I just stuck this in the calculator, and I put it in this format, and did the solutions, and it came out with giving me I1 is equal to negative 3 over 310, and then I2 gave me positive 7 over 310, which negative 3, that's 9.68 milliamps, negative 9.68 milliamps. And then I2, let's see, that's 7, gives me 22.6 milliamps, positive. Okay, so that for me was much, much simpler because then I just had to take that, stick it in the calculator, and it gave me these answers, and these match what I came up with when I did my LT Spice simulation earlier to make sure that I wasn't going to screw this up. And then we look at this again and take that intuitive understanding as our last step to make sure that this makes sense. So we were expecting a positive number for, oh crap. Ah, dang it, I did that backwards. That's wrong. That's I2, I1. I read my output wrong. So I1 is 22.6 and I2 is negative 9.68. Sorry about that. See, this is why we double check, because negative I1 should be positive, and that made me check and realize that I read this backwards because it gave me I2 first and then I1 second for some random reason. So I1 is positive 22.6 milliamps through there, and negative 2 is negative 9.68 milliamps that way. So we know that it's actually a positive 9.68 that way. And so we know that since these are mesh currents, if we want to know the actual current this way through R3, which we can just call I3, then we know that is just 22.6 plus 9.68 milliamps. And now we know the current through R3 because we know that mesh current going through that resistor, and we know that current going through there. And since we know that I1 and I2 in this case are opposing each other, it is I1 minus a negative I2 to give us our I3. So that was our last step, is just looking at it, making sure that it all made sense. We were assuming somewhere in the tens of milliamps. I figured between 10 and 30 milliamps, so that's about right. And now we know that this is right. We've gone through all the steps. We feel confident about our answers. And even if our answers aren't right, at least they make sense. At least if our teacher said, hey, what in the world were you thinking? You'd say, well, you know, at least it was in this area and I was trying, and that's where I screwed up my math. And in my experiences, teachers generally are pretty understanding about that sort of stuff, even though they will still dock you, but at least they won't completely crush you. So hopefully that was a good overview of KVL. Again, all of this stuff is on circuitbread.com. The link is in the description. Go check it out to get more samples, to get better explanations and all of this. And it's gonna help you out because, again, you need some time to go over it, make sure it's nice and intuitive. So please go check that out. If you like this, please give the video a like, subscribe to our channel, and keep on following us as we continue through our Circuits 1 or our basic circuits tutorials. Have a good one.